On July 15th, 1965, the sterile silence inside the Mission Control Center felt electric, thick and heavy like the air before a thunderstorm. Data streamed in from the Mariner 4 spacecraft, but it wasn't pictures yet. It was a cold, lifeless flood of zeros and ones. The slow computers of that era would take hours, maybe even what seemed like forever, to turn those numbers into an image. The weight grew unbearable. Then the engineers, those same people managing a multi-million-dollar interplanetary mission, did something completely unexpected. They left the lab and went to the nearest art supply store. They came back with a box of ordinary pastel chalks. On the floor, they rolled out massive sheets of paper covered with printed numbers. Then, dressed in their crisp white shirts, these grown men knelt down. They began to color. Each number represented the brightness of a single pixel. Dark gray, light gray, black, white. Stroke by stroke, with the chalk scraping against paper, the very first image of another planet in human history was born. Right there on the floor of that room. Let's start with this simple, handcrafted portrait. The very first glimpse of a world that lived in our imagination for centuries. Then, step by step, we'll piece together the story of a geological crime scene the size of an entire planet. A scar stretching across a continent and a volcano towering 3 times the height of Mount Everest hint at a disaster beyond anything we can imagine. Finally, we'll dive into the analysis of a controversial signal discovered in 1976. An experiment that revealed signs of life, but whose findings science chose to ignore for nearly 50 years. This story isn't just about rocks and ice. It's about how the desperate search for another world forced us to finally understand our own. Mariner 4 passed just 9,846 kilometers from Mars, a triumphant end to a long journey. For centuries, humanity's brightest minds stared through telescopes, seeing what they wanted to see. Polar ice caps melting in summer meant water was there. Dark spots shifting with the seasons meant vegetation grew. Astronomer Percival Lowell even sketched a network of artificial canals, built by an ancient, dying civilization to irrigate their desert cities. It was a grand dream. Mars was our romantic mirror, old, wise, yet still alive. But in that room, filled with engineers clutching chalk, that dream died. When the last square was shaded in, they stepped back and looked at their creation. They didn't see a blossoming civilization. No oases or canals. They saw a pockmarked wasteland, cold, lifeless, indistinguishable from the moon. The images from Mariner 4 shattered a century-old myth and replaced hope with a harsh, undeniable fact. That first glimpse was supposed to be the end of the story, the final chapter in our Martian dreams. Instead of a complex world, we found a simple, barren rock, a crushing disappointment in the history of space exploration. But then something strange happened. Instead of turning away, humanity became obsessed with Mars. This cold, lifeless landscape didn't repel us. It pulled us in with a strange, powerful force. It was as if beneath the dust and craters lay a mystery far deeper than any old legends about ancient canals. The first image didn't answer questions. It erased the old ones and posed a new, urgent question. Why did this seemingly lifeless rock drive humanity to spend billions and wait decades for a single chance? The answer doesn't lie in what Mars has become. It's in what it could have been. We aren't drawn in by rusty dust or a scattering of craters. Instead, we're held by a series of nearly impossible coincidences. Coincidences that make that distant red dot eerily feel like home. The first of these is rhythm. A Martian day called a sol lasts 24 hours and 37 minutes. Just a little longer than ours by about half an hour. Any internal clock, any biological rhythm tuned to Earth's cycle would hardly notice the difference on Mars. This isn't just a dry fact from an astronomy textbook. It's a connection at the deepest level. On a planet where everything is turned inside out, thin air, rusty soil, a weak sun, time flows just like it does here. That familiar pulse, marking seconds in the very heart of a foreign world, hooked our imagination first. The similarities go even deeper. Mars is about half the size of Earth, and at first it looks like a mere dwarf next to our planet. But remove the water, and the scale flips entirely. 70% of Earth is covered by oceans, vast, impenetrable to us. On Mars, the land area nearly matches the combined landmass of all Earth's continents. Africa, Eurasia, both Americas, Australia, and Antarctica all fit within the surface of the red planet. For land-dwelling creatures, for a civilization that builds roads and walks solid ground, Mars offers space on the exact same scale. It's no surprise that Mars remains the only planet where we've sent roving vehicles. The only other world in the solar system with continents you can travel across on wheels. Not just a boulder in space, but an entirely new world. Reaching that distant light pushes the limits of what's possible. Space isn't empty. It's a vast, intricate clockwork, and we're caught between its gears. Earth and Mars race like two rockets on separate lanes of a giant racetrack. Earth speeds along the inner, faster lane. Mars crawls on the outer, slower one. To send a probe, you can't aim where Mars is now. You have to target an empty spot, where Mars will be months from now. It's like throwing a paper airplane from the window of one speeding car into the window of another. And that window only opens for a couple of weeks every 26 months. Miss it by a day, and you wait 2 years. Every mission runs on a timer that never stops ticking. Sometimes the planets get a bit closer. In 2003, that distance shrank to a record low of 56 million kilometers. A cosmic gift that won't come again until 2037. This closeness, this similarity, the length of a day, solid ground, even faint traces from a time when the planet had a thick atmosphere, a magnetic field, and liquid water, all of it combined to turn Mars into a reflection of Earth. A perfect mirror, but one that's warped and dusted with rusty red soil. It's no surprise that the first people who peered at it through telescopes didn't see what was really there. Instead, they saw their own hopes. In the 17th century, these hopes first took shape on paper as the cold light of a distant world reached the lenses of primitive telescopes. Astronomy back then demanded incredible patience. Scientists spent hours freezing in unheated observatories, peering at trembling images through a murky, flawed glass. Christian Huygens pressed his eye to the eyepiece of one such instrument and made the first ever sketch of Mars's surface. Through optical distortions, he traced a dark spot standing out against the rusty background. A vast basalt plain we now call the Great Syrtis. Then, in 1666, Giovanni Cassini spotted dazzling white patches at the planet's poles. Polar ice caps. Ice meant water, and water to human minds always meant life. The trap snapped shut. Earth's reason began confidently filling in the alien landscape in its own image. The dark patches that Huygens sketched didn't stay still. From one season to the next, they shifted shape, pulsed, expanded with the arrival of Martian spring, and then contracted during the harsh winter. A wave of darkening crept from the poles toward the equator, almost as if responding to melting ice. To astronomers, the conclusion seemed obvious. Dense forests, or endless seas, their outlines changing under powerful tides and wild seasonal vegetation. Scientists even began drawing detailed maps of these imagined oases. But here's the psychological twist. While looking deep into the void of space, researchers saw nothing but a reflection of their own planet. The human brain, wired to expect Earth's seasonal cycles, flatly refused to accept an alien, inorganic logic. The chaotic dance of massive dust storms, carrying millions of tons of dark sand, was mistaken for the bloom of Martian flora. Humanity found itself trapped in a vast optical illusion. Born from a deep-rooted anthropocentrism, an unshakable belief that the rules of our biosphere apply everywhere, without exception. This cozy illusion began to crumble with the dawn of interplanetary travel. In 1971, the Mariner 9 spacecraft made a historic breakthrough, becoming the first man-made object to orbit another planet. But instead of a thriving biosphere, the probe found a global dust storm shrouding the entire globe in an impenetrable yellow veil. When the storm finally settled, its cameras revealed a world utterly dead, scarred by countless meteor craters. No forests, no seas. Just bare rock. Yet orbit provided only a safe, distant view. To face reality head-on, explorers needed to touch the surface. The Soviet Union stepped up to meet that challenge first. The descent module from the Mars 3 station pierced the Martian atmosphere and touched down right in the middle of that very dust storm. It was an incredible feat of engineering, but it ended almost instantly. Data transmission lasted exactly 14 seconds. 14 seconds of garbled gray static on the monitor screens, and then a deafening, endless silence. The craft was lost. Those brief seconds delivered a harsh reality check. The environment here was ruthlessly hostile. The planet rejected outsiders, effortlessly grinding even the most advanced machines to dust. The stakes for future missions suddenly soared to their highest point. 5 years later, on July 20th, 1976, the American lander Viking 1 plunged toward the Martian surface. Its descent wasn't just a complex math problem, it was a direct hand-to-hand fight with the physics of an alien world. Mars's atmospheric pressure sits at just 1% of Earth's. This thin, almost ghostly gas envelope consists mostly of carbon dioxide. The air is so thin that massive parachutes barely slow down the multi-ton metal craft. There's almost nothing for the canopy to push against in this near vacuum. The heat shield glowed white-hot, slicing through the upper atmosphere. Then came the parachute release and a free fall. The braking engines roared to life, burning fuel in a desperate bid to kill speed before impact. Every second of the descent was a survival gamble on a planet that had already proven it could destroy robots. Finally, the landing legs slammed into the rusty ground. The signal shot out into the void of space, traveling millions of miles to bring Earth news of the very first completely successful landing. The Viking lander's camera slowly descends. Rust-colored dust, kicked up by the braking thrusters, drifts down gently onto jagged rocks. The landscape lies utterly lifeless. No sign of movement, not a drop of moisture, not a single sprout of the vegetation scientists desperately searched for through their telescopes. Yet inside the lander's metal shell, a small automated instrument just began detecting something impossible. Now all that remained was to decode the data, to discover what exactly it had found in this frozen wasteland. Inside the metal shell of the Viking lander, a surprisingly simple experiment unfolds. A robotic arm scoops up a pinch of rusty Martian dust and places it into a tiny chamber. No complex lasers, no microscopes. The test's logic is almost culinary. If microbes lurk in the soil, they should be hungry. Scientists back on Earth prepared a treat, a nutrient-rich solution, an energy drink for microorganisms, but with a twist. This soup contains radioactive carbon. Not dangerous, just tagged like a bell on a cat's collar. If microbes eat and start breathing, they'll exhale this marked carbon, and the sensitive gas detector inside Viking will catch that signal instantly. The plan was flawless in its simplicity. Feed the Martian soil and listen for its breath. Data started coming in. Millions of miles of icy emptiness couldn't drown out this signal. On the flight control center screens, the graph crept upward. Slowly but steadily, the detector registered a surge of radioactive gas. Again and again. There was no doubt. The soil was breathing. It absorbed nutrients and exhaled a metabolic byproduct. This wasn't just a chemical reaction. The activity chart matched exactly what you would get running the same test on a handful of Earth from any garden on our planet. On the monitors, proof of life. A pulse where there shouldn't have been one. Both Viking landers, separated by thousands of miles, reported the same result. Mars was alive. For a few hours in 1976, humanity was no longer alone in the universe. But science demands absolute certainty. There was always a chance this was just strange, previously undocumented inorganic chemistry, an exotic reaction of some Martian mineral with water. To rule out that possibility, they designed a control test, the final nail in the coffin of skepticism. The Viking lander collected a fresh soil sample and heated it to a high temperature. It sterilized the sample. Any known form of life would have died from that. If the reaction was biological, it should stop after sterilization. If chemical, it might still continue. The robot added nutrient solution to the now dead baked soil. This time, silence. The reading stayed flat. No gas was released. The breathing stopped. This was the definitive proof. The test worked perfectly, proving that something in the Martian soil could be killed by heat. Something alive. And here the story takes its harshest twist. On board the Viking lander, there was another instrument. A gas chromatograph mass spectrometer. Its mission was simpler, not to hunt for breath, but to search for bodies. It looked for organic molecules, the building blocks of life as we know it. But this instrument found nothing. Absolutely nothing. Empty. The scientific community faced an unsolvable paradox. One experiment shouted, "Life," while the other answered with cold silence. Imagine hearing a choir singing behind a locked door, then opening it to find no one inside. The sound exists, but the source does not. In the end, scientists made the most cautious, conservative choice. They trusted the chemical analyzer over the biological test. The official verdict declared the positive results came from unknown exotic perchlorate chemistry in the soil, not biology. The door to Mars cracked open for just a few stunning weeks, slammed shut. Instruments picked up a faint trace of life, but scientists dismissed it as a misinterpretation. Chemistry had fooled biology. Yet soon it would become clear that the planet itself holds evidence of a physical disaster on a scale Earth has never seen before. What could have shattered an entire world? The mystery of elusive life gave way to tangible proof, a clue the size of half a planet. Mars's topographic map doesn't resemble any map on Earth. It looks like two separate worlds crudely stitched together along the equator. The northern hemisphere stretches out as a smooth, low plain, as if someone had ironed it flat with a giant press. The southern hemisphere is the exact opposite, ancient, rugged highlands covered in craters, old and battered. This dividing line, the Martian dichotomy, is so sharp and unmistakable it almost feels artificial. The planet seems to have a split personality, one half young and serene, the other bearing scars from billions of years of cosmic bombardment. Two faces turned toward opposite directions in time. This anomaly doesn't come from a slow geological process. It traces back to a single moment of absolute violence in the youth of our solar system. The leading theory? A colossal collision. A young, still malleable Mars was struck at tremendous speed. Not by an asteroid, but by something far larger. A protoplanet the size of Pluto. The impact wasn't head-on. It glanced along the northern hemisphere, stripping away trillions of tons of crust like peeling skin from a fruit. The energy released dwarfs anything the human mind can imagine. Rock vaporized instantly. The shockwave rippled around the entire planet, making it ring like a bell. And the entire northern region of Mars? It's not just a plain. It's the largest impact basin in the solar system, a giant crater, a scar that hasn't healed in 4.5 billion years. Catastrophe gave birth to a world of exaggerated extremes, a world of stark contrasts. The greatest elevation difference on Earth, from the depths of the Mariana Trench to the summit of Mount Everest, measures about 20 kilometers. Impressive. But on Mars, that range stretches to nearly 30 kilometers. 29 to be exact. Imagine this. On our planet, Everest resting at the bottom of the deepest ocean trench, yet its peak would still tower 9 kilometers higher than it does now. Traveling from Mars' lowest point, the Hellas impact basin floor, to the peak of Olympus Mons is a climb through elevations unimaginable on Earth. Our planet's crust is dynamic and alive, smoothing out such extremes. Mars's crust, cold and dead, preserved them forever like a fly trapped in amber. This split shaped the entire future of the planet. The impact didn't just carve out a lowland, it thinned the crust in the north and unleashed enormous stress deep below the surface. The planet was wounded, and like any wound, this weak spot became an escape valve for internal energy. The collision tore through the crust and forever leveled the northern land. But the real giants awoke in the south. They grew to unimaginable heights in a world where tectonic plates never shifted an inch. The southern hemisphere became a stage for geological giants, born in a world of complete tectonic stillness. The most famous among them is Olympus Mons. Long before space probes existed, astronomers spotted a strange bright patch on Mars's rusty surface through their telescopes. They called it the Snows of Olympus, convinced they were seeing high mountain glaciers. It took centuries and orbital spacecraft to reveal the truth. That bright spot is actually a shield of solidified lava, towering 21 kilometers high and stretching 600 kilometers across at its base. This lone mountain could easily cover the entire area of France or Spain. Standing on its summit shatters any familiar sense of height. Olympus Mons' slopes are so gentle and vast that because of the planet's curvature, they disappear far beyond the horizon. Standing at the crater's edge, you can't see the base. The atmospheric pressure here drops close to zero, and the sky above looks nearly black in daylight. Around you, there are no sharp peaks or sheer cliffs, just an endless basalt plain dusted with a thin layer of reddish powder. It feels like standing in open space, not on a mountain. Olympus Mons is so vast that its peak pierces through the Martian atmosphere. When massive dust storms rage below, shrouding entire continents under thick clouds, the summit stays crystal clear, rising above the chaos like a silent island in a stormy ocean. The colossal size of Martian volcanoes boils down to one fundamental fact. Mars has no moving tectonic plates. On Earth, the crust constantly slides over deep reservoirs of molten magma, like a metal sheet passing over a gas flame. The magma melts through, building a volcano. Then the plate shifts and a new volcano forms nearby. This is how long chains of island volcanoes arise on our planet. But Mars' crust is frozen in place. It's locked rigidly over a mantle heat source. The mantle plume acted like a giant blast furnace that never shut off. For millions of years, boiling rock struck the same spot, layer after layer, pumping liquid stone onto the surface. The mountain grew both upward and outward, swelling under its own weight like a stone blister. Plate tectonics on Earth is more than slow continental drift. It's a vital pressure valve, releasing the planet's inner tension. Mars lost that safety valve, and all the fury beneath its surface erupted in the form of solitary giants. The planet paid a terrible price for this unchecked growth. Billions of tons of the heaviest basalt piled up in one region, on the volcanic Ferza de Plateau, and pressed down on the crust with such force that the rocky shell simply couldn't hold. 3.5 billion years ago it cracked, with a deafening roar, giving birth to the Valles Marineris. Earth's Grand Canyon would easily get lost in one of the side branches of this scar. The canyon stretched for 4,000 kilometers, the distance from Lisbon to Moscow, ripped apart by an unbroken chasm. The canyon's width reaches 600 kilometers, and you could lower Mount Everest into its depths with a whole kilometer to spare above the snow-capped peak. The fracture plunges as deep as 10 kilometers. These canyons didn't form from flowing water or wind erosion. They're a colossal, ragged wound on the very skin of the planet. Mars was literally tearing itself apart under the unbearable weight of its own volcanoes. To descend to the bottom of Valles Marineris is to enter eternal shadow, where sheer cliffs block the sun and landslides the size of entire countries tumble down the slopes. The scale of this geological upheaval proved so immense that scientists continue to uncover its hidden victims even today. In March of 2024, satellite data forced researchers to redraw the maps of the region. For decades, a massive new volcano stretching 450 kilometers across hid in plain sight. It blended seamlessly into the rugged terrain, appearing as nothing more than a scattered collection of hills. This perfect camouflage stemmed from the same tectonic forces at play. Relentless fault lines that created the Mariner Valleys cut right through the mountain, tearing the ancient volcano apart. Its slopes collapsed into the newly formed chasms. The central caldera warped beyond recognition, and what was once a majestic peak became a shattered maze of ruins. Ravaged landscapes, frozen lava flows, and shattered mountains had told the story of a long-cooled world for centuries. The largest volcanoes in the solar system stood as silent monuments to ancient times, thought dead and frozen in eternal stillness. That certainty held firm until the day the planet began to shake, forcing this dead world to come alive again. The illusion of complete tectonic stillness didn't shatter on Mars itself. It broke right here on Earth, amidst the endless icy wastelands of Antarctica. A massive asteroid slams into the Martian plain with deafening force, piercing through the rusty crust. The impact sends chunks of rock soaring high, well beyond the weak pull of the red planet's gravity. Basalt fragments become silent cosmic wanderers, drifting through the frozen void for millions of years. Eventually, by chance, their paths cross with the gravitational pull of our world. A fiery streak screams through Earth's dense atmosphere. Blackened and scorched by friction, the stone crashes onto the dazzling white shell of the South Pole. Millennia later, a scientific expedition scanning the glaciers spots this dark, contrasting scar. Today, laboratories around the globe carefully preserve more than 300 Martian meteorites, direct physical messengers from our neighbor, locked in their crystalline lattice with the exact chemical signature of a distant alien interior. For a long time, those charred rocks simply supported the idea of a world frozen forever. Geologists dated the minerals and kept finding the same expected numbers, billions of years. Then electron microscopes caught samples that upended fundamental science. Isotope analysis revealed that some Martian meteorites crystallized from molten magma just 180 million years ago. To us, that sounds like an unimaginable stretch of time. But in the life of a planet, it's practically yesterday. Mars is half the size of Earth, and by all laws of physics, it should have lost its internal heat quickly, turning into a solid block of ice. Yet 180 million years ago, when giant dinosaurs roamed Earth and the Atlantic Ocean was just starting to open, the red planet was alive. At the very moment Mars was thought to be a long, frozen, lifeless rock, volcanoes raged fiercely. Boiling lava flowed across its surface, creating fresh basalt fields beneath a thin orange atmosphere. The planet did not die in the distant past. Stone clues from Antarctica's ice demanded direct, on-site verification. At the end of 2018, the InSight lander gently touched down on a dusty Martian plain. This machine had no wheels for long treks. It carried no mast with cameras for sweeping panoramas. Its only mission was to listen to silence. A robotic arm carefully placed an ultra-sensitive seismometer on the rusty soil, so precise it could detect vibrations smaller than a hydrogen atom. A heavy dome covered the delicate instrument, shielding it from wind noise and sudden temperature swings. It was like a doctor pressing a stethoscope to the chest of a patient in a deep coma. Nobody at Mission Control knew if the device would pick up a single sound beneath that dead rock. Silence stretched on for months. Then the ultra-precise sensors caught a faint, low rumble. Over 4 years of constant watch, InSight recorded more than 1,000 Marsquakes. The lifeless geological monument was, in fact, a living organism with a clear, if subtle, internal heartbeat. Every tremor in the crust told a story about the activity happening deep within Mars's pitch-black interior. Seismic waves passed straight through the planet, bouncing off the mantle and the molten core. Physicists expected the source of the quakes to be the Tharsis region, where massive dormant volcanoes pressed down with tremendous weight on the crust. But the strongest shocks came from somewhere completely different: the Cerberus fossae system of deep fractures. There, no towering mountains rise. Instead, fresh tectonic cracks lie hidden beneath the flat surface. These fissures stretch for thousands of miles, slicing through young lava plains like giant claw marks. Within these shadowy mazes, magma still moves slowly, tearing the rocky shell apart from the inside with a deafening grind. This discovery forced scientists to rewrite the fundamental laws of planetary science. Early mathematical models claimed that small celestial bodies lose their internal heat quickly and permanently. Mars proved them wrong. Planets cool down much more slowly, clinging desperately to traces of their primordial heat for billions of years. Deep beneath Mars's frozen sand, its core continues to resist the cosmic cold, pushing scientists to rethink even our predictions about how Earth's interior will cool in the future. A stark contrast shapes a unique paradox between the planet's blazing core and its outer shell. Deep inside, heat still simmers, enough to melt rock and unleash powerful seismic waves. Yet on the surface, the sky itself freezes every winter, wiping out a third of the entire planet's atmosphere without a trace. On Earth, winter is simply water changing its state. Frozen crystals fall from the sky, blanketing the ground in white. Yet the air we breathe stays right where it is. Mars doesn't follow this rule. Its winter shatters that pattern, turning seasonal change into a climate collapse. When temperatures at the poles plunge to minus 125 degrees Celsius, even the sky freezes. For decades, astronomers stared at the dazzling white patches on top of Mars's red surface. They were sure they saw massive deposits of carbon dioxide ice. Dry ice seemed like the only reasonable explanation for a world that had long lost its liquid rivers and seas. But modern orbiting stations, equipped with powerful penetrating radars, scanned Mars' polar caps in detail and revealed something very different. The core of Mars' ice caps is ordinary water ice, the same stuff we use to build snowmen and that fills our oceans. The dry ice, the frozen carbon dioxide from the atmosphere, only forms a thin, deceptive layer on top of this watery mass. This thin shell hides a mechanism of unprecedented power, one unlike anything else in the inner solar system. Every Martian winter, as one of the poles plunges into the darkness of a long polar night, the cold becomes so overwhelming that gas can no longer stay gas. Carbon dioxide, the main component of Mars's atmosphere, literally crystallizes in the icy void and falls like heavy flakes. Over the course of winter, up to 30% of the atmospheric carbon dioxide freezes out, forming a layer as thick as 3 feet at the poles. A third of the entire planet's air simply vanishes from the atmosphere, settling onto the rocks. This triggers massive pressure swings on a global scale. Air masses from the opposite, warmer hemisphere rush into the newly formed vacuum at the speed of a fierce hurricane, lifting rusty red dust thousands of miles into the sky. In spring, as the sun returns, this layer, sometimes a meter thick, doesn't melt. Instead, it sublimates, instantly turning back into gas, roaring out from beneath the surface and bursting through a web of cracks in the icy crust. Climate scientists studying Earth's ice ages watch this process with bated breath, recognizing it as an extreme, push-to-the-limit version of atmospheric cycles. Beneath this pulsating carbon dioxide crust lies a true treasure of a lifeless world. Water ice has built up at the poles for millions of years, layer upon layer, recording the history of Martian storms and warming periods, like the growth rings of a giant tree. Radar scans reveal that these deposits stretch several kilometers deep. If some invisible heat source suddenly melted the polar reserves, Mars' rusty wasteland would transform beyond recognition. The ice at the poles holds enough water to cover the entire planet with a 35-meter-deep ocean. This isn't just scattered puddles and crater bottoms, it's a continuous, vast expanse of water, rising as high as a 10-story building, flowing around every rock, every valley, every basalt plain, from the equator to the high latitudes. That water didn't vanish into deep space or evaporate under relentless solar winds. Instead, it remains trapped and cold, locked in permanent frost across the planet's peaks and depressions. Billions of tons of water wait patiently, in absolute silence for their moment. Massive pressure from kilometers of frozen water, combined with intense internal heat detected by ultra-sensitive seismometers, creates perfect conditions for another paradox. Beneath Antarctica's thick ice shell lie hundreds of deep lakes, where water stays liquid thanks to crushing pressure and geothermal warmth from below. Mars's poles, harboring frozen oceans, face the same physical forces. Orbiting radar probes, sending radio waves through the ice, began returning strange signals, signatures of the boundary between solid rock and dense liquid. But if frozen water hides beneath the poles, could any of it remain liquid in such a frozen world? In 2018, just when hope of finding liquid water on Mars was fading, the radar on Mars Express sent a signal that stopped scientists in their tracks. Deep beneath the southern polar ice cap, a mile beneath the frozen surface, the instruments detected an unusually bright reflection. On Earth, such a signal only comes from the boundary between ice and a substantial body of liquid water. The scientific community erupted. Beneath the frozen shell of a dead planet, an entire lake lay hidden. Not just damp soil, not tiny pockets of brine, but a full-fledged reservoir shielded from the cold vacuum of space and cosmic radiation. Our imagination conjured a dark, still world where water sloshes under immense pressure, warmed by residual heat from Mars's core, possibly for millions of years. This was more than an oasis. It was the last, most reliable cradle where life might have survived, retreating from the surface billions of years ago. Science rarely fulfills our dreams. Instead, it cuts through illusions with ruthless precision. In June of 2024, a study put an end to this particular spark of hope. Researchers showed that the radar signals, once thought to indicate water, actually come from layers of incredibly dense, compacted ice mixed with dust. The illusion melted away. But this wasn't a failure or a mistake. It was a pure victory for the scientific method. Relentless, skeptical, demanding proof even for the most tempting discoveries. That lake beneath the glacier? Most likely just a mirage. The ghost of water receded, leaving behind a cold, undeniable truth. If we want to find traces of life on Mars, we have to look not to the present, but to the fossilized past. The Perseverance rover is working to unravel this ancient past today. Its wheels crawl slowly across the floor of Jezero Crater, a place that wasn't a crater billions of years ago, but a deep lake fed by a flowing river. The rover carefully examines deposits of an ancient delta, drills into rocks that were once ordinary mud at the bottom of a stream. It's not searching for water itself. Instead, it hunts for its chemical fingerprint, complex organic molecules preserved in compressed clay. This mission answers a mystery left by the Viking landers in 1976. We still don't know if life ever left a trace there, but now we're looking in the most logical place possible. Meanwhile, sometimes from orbit, just at dawn, a faint haze appears in the vast canyons of the labyrinth of the night. It's a morning mist of ice crystals rising over fractures that stretch from Kiev all the way to Greenland. This mist is a faint echo of a lost grandeur, a reminder of a time when Mars had a thick atmosphere and real rivers raced through these canyons. This, ultimately, is the goal of our long journey to the Red Planet. Mars is not a backup home. It's not a future colony. It's the most detailed and haunting laboratory of planetary death available to us. Every grain of rusty dust, every dried-up canyon, every extinct volcano tells a chapter in the story of how a living, warm, wet world can lose everything. Its magnetic field, its atmosphere, its oceans, and turn into an icy, mummified desert. We send complex machines there not out of mere curiosity. We do it to read the planet's self-destruction manual and to make sure we never follow the same path. What began as a simple hand-painted image took us to a deeper understanding of our own fragile home. By studying the dead Mars, we learned to cherish the living Earth,